we're going to discuss the conservation of energy. Last time we talked about conservation of momentum, and we define momentum as a sum of all particle mi times the velocity vi, which is a vector. And before collision you have the velocity vi, and after the collision, and we're talking possibly multiple collision of multiple particles, you will have mi of ui afterwards. And conservation of momentum says that in the absence of an external force, what you have is that these two quantities before and after are preserved. Now today we're going to talk about conservation of energy, and what we have is basically the sum of all the particles of 1/2 of mi vi, but you take the magnitude, squaring it, and if in fact kinetic energy is conserved, then you have this equation which is 1/2 of mi, and after the collisions you have ui square, and the quantity on the left hand side and the right hand side will be conserved. Now you have conservation of energy if collision are elastic. Very much similar to what we talked about before. If two particles are having elastic collision, then if this is moving, this will stop and impart the same velocity to the other particle. So what you had kinetic energy before on this particle has zero kinetic energy, and then the kinetic energy will be totally imparted to the other particle because the velocity is transposed from this particle to the other particle. So in that case, you have a trivial case of conservation of energy. But what if you have relative motion and then you collide and the resulting velocity is not totally zero? Then we need to look at that example. Now let's prove that kinetic energy is conserved if all collisions are elastic. Now there are plenty of elastic collisions. For example, in an ideal gas where the gas comprises molecules that are colliding with each other, and these molecules are considered elastic in the collision, you would have conservation of kinetic energy in this whole process. So if you have a volume of gas and the ideal gas particles are considered completely elastic in the collision, the sum total of the kinetic energy of all gas molecules will be conserved. It would not be changed in that case. All right, the proof is not that very hard. What you have here is that, let's consider I equal to 1 and 2. That basically you have two particles. What you have done is 1/2 of m1 v1 square before the collision plus 1/2 of m2 v2 square is equal to 1/2 of m1 u1 square after the collision plus 1/2 of m2 v u2 square. If in case kinetic energy is preserved, there's no change of the kinetic energy either into heat or into sound or into gravitational potentials, because there's a gravitational field. There's no conversion of that energy into any other form, and you will have the equation here. Now, how is this proved? Well, this is proved very simply. If you rearrange the equation, so it's 1/2 of m1, and then you have v1 square minus u1 square on this side, equal to 1/2 of m2 of u2 square minus v1 square. we need to prove that it's equal. And we'll show that it's going to be equal by further factoring these two into V1 plus U1, and then you have V1 minus U2. This is simply factorization, and then you have M1 half of M2 of U2 plus V1 times U2 minus V, I think V2 here. All right, so we have that. Now, if you, I'm sorry, this is U1, and this is U2 minus V2, plus V2, and U2 minus V2. Okay, so we have it all corrected here. Now, what you have here, if I look at the term, first of all, what you have is the notion that momentum conservation you have M1 V1 minus U1 is equal to M2 of, in this case here, U2 minus V2. Well, because you can simply rearrange the terms, this is true simply because M1 of V1 plus M2 of V2 is equal to M1 of U1 plus M2 of U2. The total momentum before and the total momentum after is preserved. So what you have here is that basically these terms which I mark in red, they are equal. So all I'm left with is the equation that this equation is true if V1 plus U1 is equal to U2 plus V2. So because of conservation of momentum, all the terms that I've crossed out is true, is equal on either side. So all I need to say is that this has to be true if this equality holds true. Now this turned out to be true very simply because if true, if collision is elastic. The reason is very simple, as we defined last time, that an elastic collision C of that is equal, as we pointed out in the last lecture, that C of R is equal to V2 minus V1 divided by U1 minus U2. And for complete elastic collision, that is equal to 1. So what you have is then U1 minus U2 is equal to V2 minus V1. That would imply the equation V1 plus U1 equal to U2 plus V2. So elastic collision implies that this equation here is true. And therefore, conservation of momentum, which result in the cancellation of the term crossed out in red, elastic collision would altogether prove that kinetic energy is conserved before and after the collision.